We're going to start subsection 7.5.2 on the properties of the expected value. Proposition 7.5.3, let x and y be random variables, let h and g be functions, and let k be a real number. First property, the expected value of k is just k. Second property, the expected value of k times a function, well, you can bring out the k. And so that's k times the expected value of h of x and y. And third property, if you've got the sum or a difference of functions, then the expected value of h of xy plus or minus g of xy is the expected value of h of xy plus or minus the expected value of g of xy. So these first three properties are properties that you probably saw in your first probability course. And in particular, the properties 2 and 3, being able to take out a constant and split things over sums and differences, that's called linearity. And so that is what the note is down below here. Properties 2 and 3 in this proposition are called the linearity of the expected value. So what I don't think that you have seen before is property number 4. And that is saying if x and y are independent, that the expected value of h of x times g of y, right, notice that these are functions of single variables now, is the expected value of h of x times the expected value of g of y. And that is a little bit of a surprising property. And we're going to prove it in the continuous case, where x and y are continuous random variables. And so let's write down the definition. Not the definition, actually. It is the law of the unconscious statistician, so Lotus, the bivariate Lotus. Expected value of h of x times g of y is, well, it's the double integral from minus infinity to infinity of h of x times g of y times their density function. So f of xy dy dx, where this f is the joint density function of x and y. Now, if x and y are independent, then we know that the joint density can be factored. So if x and y are independent, x and y, we know that f of xy can be written as the product of the marginals, f sub x of x times f sub y of y. So we're going to use that here. So we can rewrite our integral as the integral from minus infinity to infinity, h of x g of y, times f sub x of x and times f sub y of y dy dx. Now we can group these things together. Minus infinity to infinity. H of x times f sub x of x. There's one function in terms of all in terms of x. And g of y times f sub y of y dy dx. Now, take a look here. We have a integrand which is factored entirely in functions of x and y. We have this over, well, it's an infinite rectangle. So I'm glossing over some of the details here, but it does actually work. And we have seen that when you've got a factored integrand over a rectangle, you can split that up. And that is what we're going to do here. So the integral from minus infinity to infinity of h sub x times f sub x of x dx and times the integral from minus infinity to infinity of g of y times f sub y of y dy, and these are exactly the univariate definitions of the expected value. So this is the expected value of h of x times the expected value of g of y. So in the next video, we will do an example where we will apply some of these properties.